Devajyoti Bera. He is an associate professor in Indraprastha Institute of Information Technology, Delhi. He received his PhD in computer science from Boston University in 2010 and BTech in computer science and engineering from IIT Kanpur in 2002. He is currently involved in active research on topics in quantum complexity, graph algorithms, and privacy issues in online services. His usual areas of research interest spans quantum computing algorithm, theoretical aspects of security and privacy, and algorithmic challenge in other domains like database, networking, etc. Apart from the theoretical computer science, he is also interested in open source development and computer systems. Dr. Devajyoti Bera has praiseworthy contributions in his research area, which includes the publication in highly standard journals and conferences, along with some book chapters and book also. Sir, with this brief introduction, we'd like to welcome you again, and I take this privilege to hand over the session to you. Sir, please.
Good morning, Dr. Jayanto. Am I audible?
Yes, clearly audible, sir.
Okay, let me share my screen. Let's see if this works out. Okay, so are you able to see my screen?
Yeah, now it has come, sir.
Okay. So yeah, so good morning you, and good morning, and thank you for inviting me. Good morning to all the participants. So this is an advanced level FDP. And I was told that the introductory session happened last year. So my task here is somewhat simple, just to remind you the basic principles of quantum computing and quantum algorithms, so that you can make sense of the more complicated topics that you're going to listen in the next couple of days, next few days. Okay. So my treatment will be somewhat more mathematical, but it all involves. So let's first. I want to first make sure that all of us understand what are the basic prerequisites. Okay, so for listening to this talk and maybe for the next 3-4 days. Okay. So if there are basic questions, please interrupt me, because this is an FDP talk. So it's important that you understand and you take away. And this being the introductory talk, if you're not completely in sync with me, maybe you're going to miss out a few interesting sessions afterwards. Okay. So what do you need to know for today's talk? So you need to know elementary probability, extremely elementary probability, elementary linear algebra, like vectors, matrices, that's all. Some of the topics of quantum computing do require a little bit more complicated aspects of probability and linear algebraic aspects like eigenvalues, spectral decompositions, UV decomposition, and even more sophisticated things. But I will not have the time to go into those today. And by and large, you would be able to understand many of the topics. I went through the schedule. By and large, you will be able to understand many of the topics if you just follow these two, and some simple complex numbers, simple properties of complex numbers. So that's all you need to know. Okay. So if you just stay with me for the next hour and 15 minutes, you will be good for the next few sessions. Okay. So you probably know that quantum computing use qubits. Okay, so let's start with qubit, but even before that, let's start with bit. So what is a bit? So a bit is an abstract quantity that can take two values. Okay, so we call it a value 0 or 1, or you could even say true or false. It's actually a two-valued variable. A bit is a two-valued variable, and a bit. So this is something we should understand right away, that a bit is an abstract quantity. A bit does not correspond to something physical. Okay, I may be using my fingers to say that, okay, if my finger is up, then I will say that it's 1. If my finger is down, I'll say it is 0. Or I may be using electrical circuit and I will say if the LED is glowing, 1. If the LED is not glowing, I'm going to call it 0. So what I'm trying to emphasize here is that a bit does not correspond to something physical. There is often, if you are not completely in the pseudocode, in a completely theoretical mindset in theoretical context. If you are a little bit more in a practical scenario, that is, you're trying to solve a problem, there is something physical whose value, there is something physical whose certain states, certain conditions, we represent them as a bit. This is important. This is not very important for a classical computing, but this is going to be important for quantum computing. Okay, there are certain physical quantities which when we measure, we say, okay, if we observe so and so, or if this is so and so, if the LED is glowing, or if the voltage is 5 volt, the voltage is 12 volt, I'm going to say that my bit value is 1. And if the voltage is let's say 2 volt, or the voltage is 0 volt, or if my LED is not glowing, or if my finger is down, I'm going to say that my bit value is 0. Okay, so there is a physical phenomena happening, and then there is this value that we attribute to it. So bit is purely a theoretical construct. A bit does not have a bit does not, it's on it itself, it doesn't tell you how it's implemented or what is the physical thing corresponding to it. So that's one aspect. Second aspect is the bit value 1 or 0 doesn't mean anything more than just that there are two states and we are defining this state to have this value. There is nothing 1 in the physical world. When we say the bit value is 1, we are not saying something is 1. Okay, we are not saying something is 0. It's just the presence or absence of two things. We are just sort of representing certain states with these values. That's all. Okay, so we are going to do the exact same thing for qubits. So let's start with first a single qubit system, a 1 qubit system. So a single qubit. So what is a bit? Just to again remind you, it is a 2-valued system which can take only 2 values, 0 and 1. 1 qubit, on the other hand, it can take infinitely many values. Why? Because it's essentially a 2-dimensional complex vector. Okay, so it's a complex vector, 2-dimensional, with norm 1. Okay, so norm is in the absolute value. Okay, so if you take any vector such that its absolute value is 1, then that essentially represents the qubit, right? So vectors, a very generic way of representing it is like a column vector, alpha beta, and we want alpha beta to be complex numbers. And furthermore, they have to be normalized, which means the square of the absolute value of alpha plus the square of the absolute value of beta. They have to add to 1. That's what it means. It's a 2-dimensional complex vector with norm 1. So that's what a qubit is. Okay. So unlike a bit, a qubit can take infinitely many values. There are infinitely many possibilities for alpha. Okay. So that's well and good. So for example, what are some example qubits? This is an example qubit, the vector 1 0, the vector 0 1, or a little bit more complicated vectors, 1 by square root 2, 1 by square root 2. Both entries are 1 by square root 2. That's also, you can just verify that if you take these are all real numbers, so absolute value is the same as the numbers, and then if you square them and you add them, then you get half plus half equals to 1. Okay, we can do actually even more complicated numbers like e to the power I pi by 4 square root 1 by 3, then I minus 1 by square root 2 by 3. If you also take the absolute value and you square them, then they add up to 1. So these are all examples of qubits. Okay, so that's what a qubit is. I mean, if you can do the entire quantum computing by simply treating treating 1 qubit as a vector, complex vector of this kind. And I'll also tell you after some time how to deal with multiple qubits. They are essentially larger complex vectors. So you can do entire quantum computing in this manner. Okay, with just as vectors, and operations will be made precise. So simple linear algebra can allow you to explore entire quantum computing. But that's not how we do it. Firstly, primarily because it's cumbersome to denote. If I have to write a qubit in this manner, it's very difficult. That's when I'm writing a program, I often say that bit b equals to 0. I would like to write these kind of things, but dealing with vectors is cumbersome. Okay, I would want to say that bit c equals to apply some function on the bit b. Now, if this function happens to be multiplication by a matrix, then again, this is very difficult to write. So we want to make some simpler representation. So what I'm going to tell you next are what are the representations. What is a very convenient, or rather not representation, but a representation. I'll only have chance to talk about a convenient one today. And then so that's the first thing I'll tell you. Second, I'll tell you is what does it mean? So we know what bits mean, right? So a single bit doesn't mean on its own too much, but you take 32 of them, you get a 32-bit 32-bit bit vector, and that's what an integer is. So we define an integer as 32-bit bit vectors. Okay. So you put together too many of bits, you put together 8 of them, you get a byte. Okay. So you put together many bits, you do a byte, and then you say that, okay, how many participants are in this FDP, I can represent them as integers, and for that I need so many bits. Okay, so there is an interpretation, additional interpretation on a bit. Depending on the context, I interpret that 1 means this and 0 means that. So now a qubit is, you can see that a qubit has these two complex numbers with a bit of constant. So I need to tell you how do I interpret a qubit? What is the meaning of a qubit? So that's the next thing. I'll tell you what is the meaning of a qubit. What is the physical interpretation? Okay. And third thing is, what do I do with a qubit? Okay, what do I do with a bit? Well, I can apply a function, a single bit function. Incidentally, it turns out there are only 4 single bit functions possible, but then you take 2 bits, you take 3 bits, you take 32 of them, you get an integer, and on integer you can do lots and lots of functions. There are lots of functions that you can do on 32-bit integers. Okay, you can exponentiate them, you can add them, you can do some Taylor series on them, you can do many things on 32-bit integers. Okay, so but even on a single bit, there are 4 functions that you can apply. So therefore then it turns out that what are the operations on a qubit, and of course this all of this is for 1 qubit, but 1 qubit, as you may expect, doesn't give you much. So I need to tell you about what to do for multiple qubits. So that's what we are going to do today. And my end goal is will be for you to be able to interpret a circuit. Okay. If I give you a quantum circuit, then I want you to be capable of interpreting it, what it means. How do you analyze what it does? How do you describe the parts, and possibly be able to have some idea how to design your own circuit for a particular function. Okay. So that's what the goal is. Okay. So let's turn to representation. So this is something that you possibly have seen earlier, maybe in earlier FTP or otherwise. So okay. So this is the familiar bracket representation. Or rather, I'm not going to go over the graph idea. So this is the ket representation. This is another representation which I'm not going to cover, the density matrix representation. That it's very difficult to combine all of them in short time. Okay, just give me a minute. After battery is blinking. Okay, I'm all set there. Okay. So So as I said, 1 qubit is a vector from a complex 2D space. Okay. So a 2-dimensional complex vector space has several bases, but all of them have 2 basis vectors. Okay. So for example, has a basis, has actually not one basis but many bases. There are many possible bases with two vectors. Okay, so a very familiar one is 1 0 0 1. This is one basis. Another one is 1 by root 2 1 by root 2 1 by root 2 minus 1 by root 2. Okay. So that's another basis. So what does it mean that this is a basis? It means if I take any vector, then I can write it as so let's take any vector x comma y, then I can write it as x into 1 0 plus y into 0 1. Okay, so I can represent it in any basis. I can also represent it on the second basis. So I'll be able to write it as, there are some x prime y primes such that I will be able to write v as x into 1 by root 2, this 1 by root 2 1 by root 2 vector, x prime into that, and y prime into 1 by root 2 minus 1 by root 2 vector. Okay, so what is the requirement? We where this x, y, x prime, y prime, they all are complex numbers. And this somewhat follows from elementary linear algebra that x square plus y square equals to 1, which also holds true for x prime square plus y prime square. Okay. So I'll leave you with a sort of simple exercise so that you can brush up your linear algebra skills. Represent or derive x prime, y prime in terms of x and y. So here is a very convenient notation that we are going to use. We're going to write this vector as this bar 0 angular bracket. This is called the ket notation. So this is going to be ket 0, and I will write this vector 0 1 as represented as a ket 1 vector. Once again, the zeros inside that bar and bracket doesn't mean anything, just a variable name. But it turns out that this variable name is chosen in a judicious manner so that it's going to make interpretation easier when we do certain things. So these 0 and 1s do not mean anything. So they are not a value 0 or anything like that. These are just representing two variable names. They just look in an odd manner, but this notation has some very nice how do I say this, implications. Okay. So this is the first one is known as ket 0, or I also sometimes use the word state 0 or state 1, and this is this 0 1 basis. This is called the standard basis. Okay, so which means now any vector, when I'm writing in a ket notation, I'm again going to use the same notation of line, variable name, and an angular bracket. So instead of this v with a top arrow, I'm going to write it as v in the ket notation. So this v, now I can write just if you're just rewriting the line above, this is x times 0 plus y times 1. Okay, so this is a general way to represent. This is a very general way to represent a state, one qubit state in the standard basis. So this is the standard basis represent. So when I say that represent a state in the standard basis, I want you to write it in terms of the state 0 and state 1 states with some complex numbers in the front, and these complex numbers in the front are called amplitudes. These are called amplitudes. Okay, and this form of writing vector, a state, one qubit state as a sum, a weighted sort of a sum over of these this state 0 and state 1 with complex amplitudes. Remember, this XY are complex. This is called a superposition. So hopefully I'll get a chance to explain a little bit more about superposition towards the end. So there is a bit of subtlety about superposition that you need to understand, but for now you can just stick to the linear algebra. Okay. So what have we done so far? We saw that I can write any state as a superposition of these basis states, state 0 and state 1. Okay. So above I also I showed that we can write this vector v also in terms of this 1 by root 2 basis. Okay, so this 1 by root 2 basis is called the Hadamard basis. This is called the Hadamard basis. So I can again do in a similar way. I can write this v as x prime, and there is a very nice okay. So there is, let me put it on the side here. Okay, so the Hadamard basis, this vector, there is a very again we have a nice notation for this because this is a very common basis vector. Okay. So that's plus and that's minus. So I can write v as x prime of the plus state plus y prime of the minus state. Okay. So when I write v as this linear combination of this plus and minus state, then this is representation in the Hadamard basis. Okay, so a very quick exercise could be that if I okay, so let's say that I give you a vector, I give you a state in the standard basis, and I can say that can you represent it in the Hadamard basis, or I give you a state in the Hadamard basis and I say that I can represent it in the standard basis. Okay, and of course, if you are slightly uncomfortable about this notation, then you should also keep the linear algebraic vector notation at the back of your mind. For example, suppose I have a state which is like this. Then what essentially means as this is e to the power I pi by 3 into 1 by root 2 of 1 0 plus 1 minus I by root 2 1 by root 2 0 1, right? So you should be able to seamlessly move back and forth between this ket notation and the linear algebraic notation until you are very comfortable with the linear algebraic notation, and then until you are very comfortable with the ket notation, and then you need not use the linear algebraic notation anymore. But until then, you need to switch back and forth, and that's important to gain a little bit more familiarity with this. Okay, so so this is the representation which we are going to use this ket notation. Okay, so the next topic is what is the meaning of a qubit? Okay, what is the physical interpretation of what a qubit is? Okay, for that let's move slightly. Let's get back to so let's talk about what a probabilistic bit is. Okay, so suppose I have a probabilistic bit. Okay, it's probabilistic bit, which means it can take two values. Again, it's a bit, so it can take two values, 0 and 1, But there are certain probabilities involved. It's not a deterministic bit. So its value is, we don't know for sure what the value is. Its value could be 0 or 1. Let's put some numbers there. Let's say it's 0 with probability 0.35, 1 with probability 0.65. Okay. So maybe then I define another bit C, which is a 1 minus B. Okay. And so what do I know about C? I know that C is 1 with probability 0.35, 0 with probability 0.65. Okay. So what you need to understand is that we do not know. Suppose somebody gives me a bit. Okay. Then the bit. Okay. So suppose, so imagine you have a coin whose bias, its probability of head is 0.65. So you toss the coin, and then you encode the value of the coin in a bit B, and then you give me C, which is again a function of that B. Now, I don't know what C is. All I know is its distribution. But as soon as you tell me, but you know what C is, because when you toss the coin, it either was head or tail, which means B was either this bit B, it was either 0 or 1, and accordingly you know what C is. Okay. So even though I do not know what C is, you know what C is. And now suppose you tell me what the coin toss is, I immediately know what C is. Okay. So even though I have a variable C which follows the distribution, okay. So what I'm trying to emphasize is that the value of C is unknown until some measurement happens. If nobody ever told me what the value of B is, or what the underlying random choice, this coin toss value was, then I would never know the value. I would still continue my whatever process that I'm doing, assuming that I have a C from a distribution. But the C actually has a value. Okay. So this value, I come to know of the value when I measure it. Now, in quantum, in qubits, we have the same kind of behavior with slight difference, but this difference is a bit subtle for me to explain right now. I'll come back to it later. Okay, so suppose I have then let me now again go back to my Kate notation. I'm now moving to qubits. So suppose I have a qubit V. Now a general qubit, I can write it as alpha 0 plus beta 1. Okay, now so until I do any measurement, I again have I do not know what the exact state is. Remember, the exact value of this qubit is a complex vector. I do not know what the complex vector is until I measure. Okay, but when I measure, something happens. Okay, now, strangely, whether you like it or not, the measurement can also happen in multiple different ways. Okay, so suppose I measure in the standard basis. What does measuring the standard basis means? It means I will first represent V in the standard basis. So that's alpha 0, beta 1. So, and then, so when I measure in the standard basis, there are two possible outcomes. Either I will see the state 0, or I will see the state 1. The state 0 will be seen with probability absolute square of the absolute value of alpha, and state 1 will see with probability square of the absolute value of beta. Okay, so that's what the interpretation is, that when I measure, I either see the state to be 0 with probability mod alpha square, or I see 1 with probability mod beta square. And just like in classical, once you know the value of C, you know the value of C. That is, from henceforth, you know that C is either 1 or 0. Same here. Once you do a measurement, the value of V, this vector, is now behaves like a deterministic vector. It is either 0 or 1. So this is called a collapse in quantum mechanics. There are interesting quantum mechanical phenomena happening behind it, but I am suppressing all of it. Okay. So this is called a collapse. When I measure the state which was alpha 0, beta 1, now collapses to either state 0 or state 1. And the probability of collapsing to state 0 is mod of alpha square. And the probability of collapsing to state 1 is mod of beta square. Okay, so now we just want to make sure that the probabilities add up to 1, but that's true because we have already seen above that when I have when I write V in the standard basis, I write it as alpha beta and mod of alpha square plus beta square equals to 1. Okay. So therefore, this sum adds to 1. Right. So the probabilities are all nice and good and preserved. Okay. That's what a measurement means. Now I can also measure there's another basis that we spoke about. This is a very common basis, but there are infinitely many bases of a complex vector space. So I can measure in the plus minus basis, or it is also known as the Adamant basis. Okay, so what do I get? Okay, so to understand what do I get in the Adamant basis, what do I have to do? I have to rewrite V in terms of plus and minus. Right, so that's the basis change, that the exercise that I spoke a while ago. So you rewrite a V, the state V, in terms of the plus or minus. So you do a basis change and you write V in terms of the plus and minus. With now I will have a different linear combination, alpha prime beta prime. Of course, again alpha prime square plus beta prime square have to equals to 1. Okay, but this allows us to understand the output of the measurement. The state will collapse to the plus state or the minus state. The probability is going to be mod of alpha square for plus state, and probability is going to alpha prime square for plus state, and it will be mod of beta prime square for the minus state. Okay, there is okay, so there is a very nice way to do this basis change also. So how do you, in general, this basis change may sound daunting, but this basis change, this basis alpha prime is okay, let me just use, okay, this is the inner product of plus and V. Remember, these are all at the back of your mind. You should understand that these are all vectors in the complex space. So I can take the inner product. So if you take the inner product of plus and V, then that's actually alpha prime, and beta prime is the inner product of minus and V. Okay, so there is a very nice notation for this inner product also. What you do is you write the first one, and you flip the sign, and then you multiply it with the second one, and again there is a nice shorthand for this combination of plus, opposite plus, and V. This notation is called bra. So this is bra plus, and this is as you know, this is ket V. Okay, and so we can this notation allows us to only write one bar. So I have this notation, this left bracket plus bar V right bracket, and this is called bracket, which actually looks like a bracket, and that's where the terms bra and ket comes from. So that's the graph story behind why do I call it bra and ket. Okay, but this is just this inner product is if you know about basis change, then that's exactly what you do. To get the coefficients, you do the inner product. Okay. Now, before I move ahead, I want to explain to you this measurement in two different bases for a single quantity is not something very, very unique here. It's easy to understand. Suppose, imagine that you have a line segment, okay, and you have a ruler, that let's say has only inch marks. Okay, so this is 0, these are all inch. This is 1. This is 2, this is 3, this is 4, this is 5, 6. Okay, so now when you see this, when you measure the line, you're going to say that it's okay. It looks like 6 inches. Okay, so that's one measurement scale. And suppose you have a scale that has centimeters, okay, so then you would say maybe this looks like 13 centimeters. So so depending on the device, a device can measure different things and can output different observations. So that's the same thing here. The single state V we can measure using different devices or in different manner, and we just get different outputs. So there is nothing sophisticated or fancy out here. Okay, we don't do that for bits and collection of bits. That's just that because we don't have any way to measure a bit in two different ways. It doesn't sort of make sense for bits because bits can take discrete values and only two values, but because a qubit can take complex values and it's a continuum, we can expect different outputs when we measure them and using different devices. That is what the interpretation of a qubit is. If there's a qubit, then there is an inherent state of the qubit, which is that underlying vector. But what you observe, you do not know if I give you an unknown qubit, you do not know the state of it. The only way you can know the state of it is through measurement. But when you measure, you don't know the exact state. Remember, when you're measuring in any of the bases, you are not getting both the complex numbers. You are getting only the square of the absolute value of one of them. That also as the probability. You are only seeing one of the states with some probability which depends on the absolute value of one of the amplitudes. So you do not even get the exact alpha. You only get mod of alpha square. So if there was a complex phase of alpha, that doesn't show up here. Okay. And second, you get this alpha not as a number. You don't see it in a voltage meter or any device. That's implicit. You get a state 0. So suppose you do this, you measure a V, you take like lots of copies of V and you measure them many times, then you expect that the number of times you get to see 0 is going to be roughly proportional to this, a number which will be close to mod of alpha square. So from there you can get some inference on mod of alpha square, some statistical tools, so that you know how close it is from the actual value. But that aside, that is the only way you know this alpha. At this alpha, you don't actually see it. So there is, in some sense, somebody can say you do not actually know what the state of a qubit is. You only know upon measurement, and that too you know certain aspects of what a V is, not the entirety. Okay, this makes designing algorithms very difficult because in classical context, in classical computing paradigm, we are used to knowing the exact value of a variable, which we cannot do here. So that's all about how do I interpret a qubit. Okay. Now let's go to the next task. What are the operations? Okay. What are the operations? Okay. So this is purely driven by quantum mechanics. A qubit is represented. So the properties that we spoke about a qubit, these properties are visible when we represent qubits as quantum level particles. Okay, photons, electrons, superconducting currents. So when we represent these qubits in terms of certain physical properties of quantum mechanical objects, then we start seeing the properties these properties that we mentioned above. Okay. So quantum mechanics tells us that these quantum mechanical properties can only be changed in certain ways, not in a completely arbitrary way. And what is the way? It is through unitary operators. So an operator is what? An operator is something that's like a plus an operator. It operates on two integers, gives me an integer. So an operator is just some function. Okay. So unitary operator is an operator that's this is a bad way of explaining, but for now it's probably going to work. That an operator that is realized as multiplication by a unitary matrix. Okay. Okay. So what is a unitary operator? So it takes So for a single qubit unitary operator, it takes a qubit. A qubit is a complex vector over C. So that means a two-dimensional complex vector over two-dimensional complex vector. So it's an element from C square. It acts on a two-dimensional complex vector and gives me a two-dimensional complex vector. So it acts on a qubit, gives me one qubit. So it changes one qubit in some manner. Okay. So what do I mean by unitary matrix? Let's just take a quick example to understand it. So suppose I have a state X, I operate U on it, and I get the state X prime. And suppose there is another state, take any other arbitrary state Y, and when I apply U on it, I get the state Y prime. Okay. Now, I explained above that the inner product of two vectors can be written in this bracket notation. It just on top, you can see it. So the inner product of this X and Y, let's look at the inner product of X and Y, this X state and the Y state. And let's look at the inner product of X prime and Y prime. Okay, so X prime, Y prime are the states that I get after I operate both a U on both X and Y. So operator is unitary if these two inner products are same. Okay. So what is a unitary operator? It's a unitary unitary operator or a unitary matrix is an operation that preserves inner product. Inner product corresponds to angles. So roughly you can also say that it preserves inner products or angles. It's angle preserving operations. So if I have two vectors that have a certain angle between them, when I apply the inner product, I'll again get two vectors which have a certain angle between them. The corresponding analog is again holds for when I say the same thing using the Ket notation. If I have two states X and Y with a particular inner product, the inner product remains same even if I apply U to both of them. So that's what a unitary operator is. So some examples of unitary operators. Okay, so there is another sort of a more operational definition, but that will maybe I'll say it out. So okay, so when you write operator as a matrix, so I can talk about the inverse operation, and then I can also talk about the dagger operation. So dagger operation is complex, is the complex transpose. So given a matrix, what is U dagger? So I take this transpose and then I take its complex conjugate. Okay. So a unitary matrix is a matrix for which U inverse is same as U dagger. So that's the more operational definition. The more meaningful definition is the one that I like more is the one with respect to inner product. It allows me to sort of visualize states as vectors and then understand what operations are. So some examples of unitary operations are obviously the identity operation is a unitary operator. Okay. It obviously preserves inner products, right? If I apply the identity operator on both X and Y, the inner product remains unchanged. But then there are some nice other operations also. So here is one operation which is fairly common. The H operator, in short, the Hadamard operator, whose short form is the short form, which is usually denoted by H. So what does the H operator looks like? The H operator, let me tell you what this operator looks like. Okay, I'm going to write it in this slightly more sophisticated form so that we can understand what does it mean. Okay, so that's what the H operator looks like. Now let's understand the meaning of it. So if I apply H on any zero, okay, so this I remember this opposite angle. This I call it as this was a Ket line, variable name, angular bracket was a Ket, and this angle, variable name, and then line. This is a bra. Right? So when I take a bra and a Ket, I get an inner product. When I get a Ket and a bra, it's like an outer product, but most important, it's an operator. So I can take the okay. So maybe I should also explain here that the bra of So this corresponds to a row vector. Okay, so our kits, this corresponds to column vector. Or states, they are column vectors. If you take the same column vector and if you transpose, then you get the corresponding bra, and you take the complex conjugate. But that's not important. So you will for what's important is that it's I can write H in this form of outer product, linear combinations of outer products. Outer products are products of a kit and a bra. Okay. So now when I want to apply it on a state, it's very easy to write it in the state. What do? I first write it, write out the operator, and then I write out the state, and then I simply multiply. I simply linearize it. I simply apply term by term on my state. Okay. So let's see it in action. Okay. Now let's try to parse this. Okay, this is a bad color. Maybe this is a good color. Sorry. So this bra 0 times kate 0. Now this bra 0 times kate 0. If you, so I can, okay. This is, what is this? This is the inner product between 0 and 0, right? So now these are two same states, same vectors, so the inner product is going to be 1. Okay, so therefore I can write the first term as plus times 1. 1 is a scalar. And what about the second term? Okay, for the second term, let's see, I have 1 bra 1 times kate 0. This is the inner product between 1 and 0. Now 1 and, remember, 1 and 0 formed an orthonormal basis, and you know that this vectors, 1 stands for the vector, I've told you that it stands for the vector 0 1, the state 0 stands for the vector 1 0, and 0 1 and 1 0 are orthogonal to each other, which means the inner product is going to be 0. So when I come back here, the scalar corresponding to the minus state is 0. So I'm only left with the plus state. So H on 0, therefore we get to be the plus state. Okay, we do the same exercise for H of 1, you will see that we get the minus state. Okay, and you do the same exercise on any other state. Any other state, which I can, let me write, take any other state, and I can write it as a complex combination of the 0 state and 1 state. So when I do that, you will see what I do. What I get is alpha times H of 0, beta times H of 1. Alpha and beta are scalars, and so this becomes alpha alpha plus beta minus. This, the reason that I could take H inside, I could, when I apply H when I apply H on a linear combination of states, I get a linear combination of H applied to the individual components of the superposition. This is because this H, the unitary operator, is linear. Linear operations have this property that you can, the operation of a linear combination is the linear combination of the operations. Okay. So what happens when I apply H on a linear combination? I get just the alpha plus and beta minus. So because of this linearity property of unitary operations, I therefore do not need to specify the value of H on every possible state. I can describe H by telling you its actions only on the basis states. So I take a basis 0 and 1. I take a basis 0 and 1, and then I tell you that, okay, H acting on 0 is plus state and H acting on 1 is the minus state, and for any other state, H extends in a linear manner. So that's what I can do. So instead of 0 1 state, I could have also given H in some of the other basis. So I could have, in that case, so another basis, the Hadamard basis. So H applied on plus, I would get, you can try it out just in the same manner I showed above. You can do the exercise and you will see that H applied on plus, you get the 0 state. H applied on minus, you get the 1 state. So I could have also told you what H is in terms of these actions on any other basis. So that's possible because H is a unitary operator which is linear. So this is a fairly common operator, the Hadamard operator. Another common example. Don't have space here, so okay. So another example is the Z operator. The Z operator is written in this manner: 0, 0, minus 1, 1. This is when I'm writing Z in the standard basis. I could also write Z in any other basis also. Okay. So now what is the action? So as if you've been following me, I said to explain an operator, I only need to tell you its actions on the vectors of on any pair of basis vectors. Okay. So for example, I could say that you can try out that Z on 0 is going to give you 0, Z on 1 is going to give you minus 1. So that is so that's the action of Z. For any other state, Z extends linearly. What does it mean? If I give any other state, any other superposition of 0 and 1, then I get alpha times Z on 0, that is 0, and plus beta times Z on 1, that is minus 1. So now you can see Z's action. Z changes the phase. It adds and it applies a minus 1 multiplicative minus 1 phase to the amplitude of the one state. That's what Z action is. So here is a very nice exercise. What is the action of Z on plus? What is the action of state on minus? These are very nice exercises. So a few other nice properties of unitary operations, which also follows from the definitions above, are that unitary operations preserve length. But this it may not be immediately clear why it is useful, because we only talk about unit length vectors. So for example, if I have a vector u, if I have a state x and I have a unitary operator u, I apply the operator on the state, the length that I get is going to be the same as the length of my state itself. Okay. So this is a unitary. This is a yeah. So this is how I evolve states by applying unitary operation. And if I give you a unitary operator and I say that okay, here is a state and here is a unitary operator, can you tell me what happens once you apply the operator? What you do is you simply multiply, where you apply the operator on each of the combination of each of the term in the linear combination, and you apply them in an individual manner and just combine them the way I have been showing. Okay, and that's how you get what happens for the resulting state of applying an operator on a state. Okay. So at this point, I can possibly tell you a little bit about some nice applications. Okay. Based on the simple principles that you have already seen. Okay. So first is that if there is a state V, okay, now any sort of measurement, if I do measurement, I'm going to do measurement in some basis. Okay, so maybe in some unknown basis. Suppose there is an unknown basis B and C. Okay, then I can only write it as alpha prime and beta prime. So there is some basis B and C, and when I measure the state in any basis, what do I get? My state collapses. I'll get either B or C with some probability. But there is a collapse that happens here. What does it mean, this collapse? It means that my state changes from the original linear combination of B and C to either B or C. So this is actually quite interesting, and this forms the basis of quantum key distribution. This is one of the guiding sort of tricks in quantum key distribution. So the idea is that you want to send, you want to send a key to someone, and you want to encode the value of the key as states, as the states. So you send multiple qubits, and each qubit represents one bit or some portion of what the key is. Okay, and now suppose Alice, instead of many qubits, I mean, this whatever I said above also holds for multiple qubits also. So suppose Alice is sending one qubit to Bob, and there is Eve in the middle with eavesdropping. And now Eve wants to find out what that qubit contains. What is the state of the qubit? Okay. Because if Eve knows the state, Eve can figure out the value of that qubit, and even if he's able to do that successfully, then Eve can do that for all the qubits that Alice is sending to Bob, and then Eve would know the key, right? Now, but what happens is when Eve tries to learn about that qubit, the state of the qubit, the only way I said anyone can know what the state of a qubit is by measurement. But Eve will use measurement in some basis. Okay. Whenever Eve does a measurement in some basis, the state is going to collapse to one of the vectors in that basis. So what Bob gets is not what Alice has said. Suppose Bob sends V, but Eve measures in this basis B and B prime. Then Bob will either get B or Bob will get B prime. Bob is not going to get what V is. Okay. So what means is that if Bob has a way of figuring out that what he is getting is different from what Alice had sent, then Bob can figure out that the qubit was tampered with. And that is exactly, so it's not done yet. It's tricky. How could even Bob figure that out? Because if Bob can figure that out, Bob can probably also figure out the key. So there are some sneaky ways the QKD protocols achieve this. But the basic idea is this: the protocols work, and the protocols guarantee against eavesdropping because of this phenomena that any sort of measurement on the way is going to destroy the state. It's going to collapse the state. It's going to change the state, and that state change is somewhat detectable at the other end. Bob can employ some tricks to detect that the state has changed, even though Bob may not know what the exact state is. And that's possible. There's some tricks to do that, but it all boils down to this idea of collapse when Eve tries to measure. Okay. There's another nice application which is regarding private database query. Okay. So imagine that you are a client, and there is a server, and then you send your question to the server, okay, in terms of many qubits. So let's just for now assume that we are sending one qubit. Whatever I say is going to scale up to many qubits also. So the idea remains same, but it's easier to understand with one qubit. I wrote 1 bit. Okay. So suppose I have Alice here, and Alice, there is a server, and Alice is sending 1 qubit to a server, which is a query. Okay. Now server computes the answer, and then server returns the answer again as response qubits. And Alice also demands from the server the query qubit, that you have to send me the query qubit back. Okay. So now, okay. So and Alice can suppose verify that the query qubit that it gets from the server is exactly the same query qubit that it has sent. Okay. Now this guarantees Alice that the server does not know what the query qubit is. So server server then what? So what the server has to do now? Server can only generate the response qubits in an oblivious manner. What does it mean? It means that it has to compute what the response is, but the server cannot actually find out what the query qubit state is. Because if the server tried to measure the query qubit would collapse. And once the query qubit collapses, the server has no way of regenerating the original query qubit. So server would not be able to send the original query qubit back. So this promise of being able to, if the server can promise that it is sending the query qubit back along with the answer response, then the server is also guaranteeing that, look, I have not looked at what your query is. This is a complete private query that you have made. You have made a query, I've given you an answer, but I don't know what your query is. So Alice gets the response without Bob knowing, without the server knowing what the question was. This is a fascinating promise. Imagine searching Google where Google doesn't know what you are searching. Okay. Now, some of you may be wondering, what if server makes a copy? What if server copies the query qubit? Okay, and makes another copy, but that's also not possible. That is also not possible. That is because this idea of copying a qubit, you can again all of this is elementary linear algebra. You can show that this is not a linear operation. It's a non-linear operation. Okay, so which means there is no unitary operation that can copy a qubit. So copying a qubit is not a linear operation, not permissible under the laws of quantum mechanics. Right? So arbitrary states cannot be copied. There's a fancy name to it. You probably have heard of it. It's called the no cloning theorem. So therefore, the server cannot copy the qubit and cannot measure the qubit. So when the server returns the response and the query qubit, Alice is confident that the server has not looked at what the query qubit is and therefore doesn't know what I'm querying. So very fascinating applications and very interesting. Many of these ideas have actually been used, have definitely been demonstrated in labs, and many of them are actually now used in commercial protocols. Okay, so now let's move to. Okay, so that's done. What is left? Okay, let's see what is left. So we have done representation. We have done the meaning of a qubit, the idea of measurement. We have seen that the operations have to be unitary. Next comes what to do with multiple qubits. Okay. Good. So now, suppose I have one qubit. Let's denote the state by V1 in 0. I have another qubit. Let's denote the state by plus. Okay. Now I want to create a combined system. I want to put the two qubits side by side. I want to create like a 2 qubit variable kind of thing. Okay. So now I am denoting this V3 for the combined 2 qubits. Which what I'm going to do is I'm going to simply write them side by side. And remember that the first state corresponds to the first qubit and second state corresponds to the second qubit. That's all I'll do. This is actually a shorthand for a linear algebraic operation known as the tensor product, which you do not need to worry about unless you want to write down the vector corresponding to V3. So if you want to know what is the vector corresponding to V3, what you will do is you will write down first the vector corresponding to V1, you will write down the vector corresponding to V2, the two column vectors, and then you will take the tensor product. So if you do the tensor product, then you can write down the entire thing, but you do not actually need to do that for understanding how circuits work. Okay. So what we'll do, we'll simply write down V1, V2 side by side, and just understand that the first state, whatever the state is, corresponds to the first qubit, second corresponds to the second qubit. Right? So there are very nice shorthands people use. Sometimes maybe I'll write this. What it actually means is I have a tensor product of two states, 0 and 1. Okay. Again, some way to this is again what is inside this ket is a string, and this is using the comma, I'm just saying that, okay, these are actually two kits put side by side. Okay, so maybe I'll also write it as 0, 1, which is also going to mean the same thing. So these are, so this 0, 1, then ket 0, ket 1, none of these are actually mathematically correct, but these are easy notations that all of us understand. And if you are reading online blogs, tutorials, you will encounter this notation. Just don't get scared. It actually is a tensor product. Okay. So for example, I can also say what is plus or minus. So now what is plus or minus? So let's write it down. So this plus is 1 by root 2, 0 plus 1 by root 2. So this is a state in the Hadamard basis. Okay, so this is a Hadamard basis representation of a 2-qubit state. Okay, and now suppose I want to represent it in the standard basis. Okay, so what do I do? Okay, so I first write down the expand plus state in terms of the standard basis. Expand the minus state in the standard basis, and then I expand linear tensor product. Tensor product is also a linear operation, which means now I can so the scalars multiply on them, and I get 0 tensor 0. Then I get half 0 tensor 1. The 0 tensor 1, the shorthand that I'm going to add, I've used here, I'm just simply going to write 0, 0. Okay, then I'll get half of 1, 0, then minus half of 1, 1. Okay. So that's the plus minus 2-qubit state, which is plus minus in the Hadamard basis. This is the representation in the standard basis. Okay. So this is the, so now you know how to represent even 2-qubit states. The same idea works for 3-qubit, 4-qubit, higher qubits also. Okay. Now, what is measurement? So suppose I have this plus minus state and I observe in the standard basis. Measurement is again in multiple bases, it can happen. Right. So to know what happens when I measure in the standard basis, I first rewrite the state, represent the state using the standard basis, which I just saw above. And then once I have this state, right, again the same idea as before. When I observe, I will see that I'll see the state 0, 0, or I will see the state 0, 1. Remember, 0, 0 is basically first qubit is in state 0 and second qubit is in state 0. 0, 1 is basically a tensor product of 0 and 1. It is saying that the first qubit is in state 0 and second qubit is in state 1. Then state 1, 0 and state 1, 1, and each with probability half. Sorry, not half, 1/4, square of it. Okay, so that's the idea of measurement. Again, it's same as in for single qubit. The same trick applies here, right? So just a quick exercise here you want to do. What happens if I measure in the Hadamard basis? Okay, and now what about operations? Okay, what about operations? Okay, so let's take an operation. So a 2-qubit operation will look like this: H cross H, which basically means apply H on first qubit. This is an example of a 2-qubit operation, and this second H means apply it on the second qubit. Okay, I could do an operation like Z cross H. I could do operation like H cross I. Okay, and they just mean that I apply the first one on the first and second on second. Let's see how do I how do I apply these operators? Suppose I do H cross H on a state, let's say plus minus state. Okay. Now how do I apply this operator on this 2-qubit state? Well, this first H, I'm going to just write H sub 1 here. H sub 1 acts on the first acts on the state of the first qubit, so the plus state. H2 is the second qubit operation, which acts on the second qubit of state minus, right? So how do I, so the way how you apply the operator, you apply the first operator on the first qubit state and second operator on the second qubit state. So first operator on the first qubit state and second operator on the second qubit state. Okay, so you can verify that H1 on plus is the 0 state and H2 and minus is the 1 state. So you get the state which I'm writing as 0, 1. That's, you see. So now you know if I have a multi-qubit operator, how do I make it act on if I have a 2-qubit operator, how do I act on a 2-qubit state? Same idea generalizes to even multiple even more qubits as well. So the last operation that's interesting, and that's all you need to understand all the circuits, that most of the modern circuits, is the CNOT gate. The CNOT gate or CNOT operator. Okay, so how does the CNOT operator look like? What it does is, again, the same thing that I happened before, because it's in a unitary operator, it's linear. So I only need to specify its operation on the basis states. So I'm going to show its operation on the standard basis state. A good exercise would be to find out its operation on some different basis, maybe the Hadamard basis. So on the 0, in the standard basis, its operations are, if it is 0, then if it is 0, 0, the first qubit is 0, second qubit is in 0, then the state remains 0, 0. The state is 0, 1, the state remains 0, 1. But if the state is 0, 0, it changes to 1, 1. If the state is 1, 1, it changes to 1, 0. Okay, so you can sort of roughly summarize it in this manner, that if the first qubit, here the first qubit is called the control qubit. If the first qubit is 0, do nothing. If the control qubit is 0, if it is not set, then do nothing. If control qubit is 1 in this state 1, then apply the X gate to the second qubit, which is called the target qubit. So that's where the controlled NOT comes. What is the X gate? It acts like the NOT gate. Okay, so X gate's operations are, it changes 0 to 1, it changes 1 to 0. It's like the NOT gate. So you see that it's flipped. If the control qubit is 0, it flips 0 to 1, it flips 1 to 0. So that's what my CNOT gate is. So if you want to again see CNOT in this manner, in the manner I was writing all the states before, if the control qubit is in 0, then do nothing on the target, and if the control qubit is in 1, then you apply the X operator. So that's what my CNOT is. So now you can verify. Now you can verify that if you apply CNOT on, let's say, 0, 1, you should get 0, 1. Okay, so that you can verify. Again, the same idea as before. You write 0, 0 cross I plus 1, 1 cross X on 0, 1, and things are linear, so you linearly apply things. You apply the first component on the state, and you apply the second component on the state, and you just use the same way I was applying before, right? So this operator acts on 0, the 1, 1 operator acts on 0, and the I operator acts on 1. Second qubit operator is in second state, and you will see that right. So the same idea as I was using before. You'll see that it's the right. It's the you will end up with the state 0, 1. Okay. Okay. So the last sort of thing is how to analyze a circuit. Okay, so suppose I give you a circuit whose qubits are initialized to in this manner. Qubits start with the 2-qubit circuit. The states are initialized to 0 and 0, and then I apply this H gate, and then I apply the C0 gate. The C0 gate is represented in this manner with this solid dot reveals the control qubit, so each line corresponds to a qubit. The solid dot reveals a control qubit, and this plus represents the target qubit. Okay, so how do you compute the final state? And let's say then I do a measurement in the standard basis. Okay, how do I derive it? How do I see what my output is? Okay, so the way to do that is to write down the states at the time t equals to 1, t equals to 2, t equals to 0. So at this t equals to 0, there's no time here. Just to say in the first phase, second phase, after every gate, every layer. So the initial state is 0, 0, which is the tensor product of 0 and 0, but this is how we are writing it. Now at t equals to 1, how do I get the state? What am I applying? I'm applying H on the first qubit and nothing on the second qubit. So nothing is same as identity. So the state that I get is H cross I, H tensor I applied on 0, 0. Again, the H gets applied on the first 0, I gets applied on the second 0. H on first 0 gives me plus, I on second 0 gives me 0. Okay, so then at t equals to 2, this will look at a bit of space. At t equals to 2, what do I get? What is this get? This is C0. This is C0 acting on this state plus 0. Okay, so now so C0, if you write it down, it is 0, 0 cross identity plus 1, 1 cross X. You could apply it on plus 0. Again, the same exercise that we were doing above. You will see what we get. But there is a simpler way of also doing the same. So you take the state plus 0. Remember C0's operations. We wrote down the operation of C0 in terms of the standard basis. So it's easier if we write down plus 0 in the standard basis. So let's just do that. So what do I get? 1 by root 2, 0, comma 0. 1, oh, sorry, not 1, 0, comma 1, but 1, comma 0. Okay. Now when I apply C0 to this is now written entirely in standard basis. What do I know? Okay. So 0, 0, the control bit is 0, so nothing happened to the target bit. So 0, 0 remains 0, 0. Why can I do this? Because C0 is linear. It's unitary operator, so everything is linear. So I can apply C0 to the first term in the superposition and second term in the superposition. Okay. So that's so the first term remains as it is, and second term the scalar is same, and the control qubit is 1, so target qubit is flipped. So I get 1, 1. Okay. Now what is this qubit? So this is after t equals to 2, and then I do a measurement. So when I do a measurement in the standard basis, so it's already written in the standard basis. Okay, what do I get? I get 0, 0 with probability half, 1, 1 with probability half. Okay, now this is an amazing thing, right? Both the first qubit and second qubit have the same value, right? And this is actually a this state is known as the Bell state. This is one of the Bell states, a very famous Bell states, very famous Bell state. And this, what it shows as this, that these two qubits, the first and second qubit, are entangled. That they are somewhat, their states are related to each other. Either I will see both of them to be 0, I'm going to see both of them in the same state. So it's either both of them 0, both of them 1. So why is Bell state very interesting? Why? Because one can, at this point, one can take the first qubit to some planet and the second qubit to another planet, maybe very far away, and then you measure, and then I mean, this is a little bit hard to show with the techniques that we developed here, but even if one of them measures, maybe in the first planet the guy measures, both the qubits are going to collapse to the exact same state, and that's a phenomenal sort of fact. Right? Because the first guy would know that as soon as the first guy was observing a 0, the second guy's state has changed to 0 magically. The second guy's state is no longer a probability, it's no longer a superposition of 0 and 1. The second guy's state this qubit has changed to 0. And that's behind a lot of very, very interesting applications, starting with QKD, but there are fabulous applications of this idea of entanglement. Okay, so this is where I'll stop. Okay, so at the end, I hope you have understood. My goal was that, so suppose someone gives you a circuit and an input and tells you what happens when I run the circuit on the input and I measure, you should be able to do that. Right? That is just like if I give you an algorithm and I give you suppose I give you a shortest path algorithm and I give you a graph and I say, okay, can you tell me what is the output of the algorithm? Just can you dry run it? That's what it is. Right? So this is a very, very, very sort of a basic skill required to understand quantum circuits, be able to design quantum circuits, that you should be able to dry run quantum circuits. And I hope, as you can see, that it all requires very basic, simple linear algebra, even the simplest notions of probability, and that's all. And with some very little practice, you can gain this expertise, the skill of being able to dry run a quantum circuit on an input. And at least that, so somebody, when you see a circuit on some blog or some tutorial or in one of the later talks, then you should be able to work out the circuit, what its operations are on the input state, and say out, okay, this is what happens when I measure it. Okay, that's what I end. Thank you. Thank you for listening.
Thank you, sir. Thank you for your valuable talk. Now I would like to invite all the participants, if you are having any ask, so may anybody, do you have a may I ask?
Okay, I can see some question regarding the multiple qubit operations. So for multiple qubits, you will be given an operator. So if the operation is something like, if the operation is a combination of single qubit operations like H cross H, Z cross H, H cross I in this manner, you have to just remember that the first operation corresponds to the first qubit, second operation corresponds to the second qubit, third operation corresponds to the third qubit, and you simply apply them you simply apply the first operation on the first qubit, tensored with the second operation and second qubit in this manner. Okay, so the way I have shown in the example here. And if you are given a multi-qubit operation like a CNOT gate, and there are similar multi-qubit operations, then you will also be given that the specification will include the how the states change for in some basis. So usually it's given in the standard basis. So you will be told that 0, 0 changes to 0, 0, 0, 1 changes to 0, 1. In that case, what you can do is the way I did it here, that you write down the state completely in terms of the standard basis. So I expanded this plus 0 state completely in standard basis. So I got the state 1 by root 2, 0, 0 plus 1 by root 2, 1, 0. And then I applied the CNOT operation. CNOT operation says that if the input state is 0, 0, then the output state would be 0, 0. If the input state is 1, 0, the output state would be 1, 1. So I looked at so these operations are linear. So that's the beauty of it, which means you can apply them on each term in the superposition in an independent manner. Right? So this 1 by root 2, 0, 0 remains 1 by root 2, 0, 0. And the 1 by root 2, 1, 0 becomes 1 by root 2, 1, 1. Right? That's how that's the easy way of applying multi-qubit operations. Did I answer the question? Any other question?
Hello, sir.
Yes, go ahead.
Sir, can I ask something related to the IBM Quantum Lab and the analyzing of the circuit part?
Yes, please go ahead.
Sir, when I calculate this particular output, like for example, I am using the teleportation circuit that is used for the teleportation part. So in that, when I analyze the circuit mathematically, I get a particular output. But when I run the same circuit in the IBM Quantum Lab, that is, or in the Quantum Composer, I get different outputs. So what is the reason behind that, sir?
So the reason behind our errors. So back in 1950 and 60, when classical computers were sort of starting, when computers were really the size of rooms, big halls, then at that point errors were very common. We don't see it these days, but there is a huge amount of error correction happening in our RAM, so that when I put something in the RAM, when I put a 1 in the RAM in a particular address bit, it remains 1, right? Because voltages drop and fluctuate, and there are errors induced from currents here and there. Huge amount is already happening in the detailed circuitry that's inside your computer chips, in your phone, everywhere. See? But we don't talk about it because now it's all commonplace. Now the technology is well established. We are right now, quantum computing is in that stage of 1950 and 60, where a qubit does not remain a qubit. The value changes after a few milliseconds or a microsecond, depending on the implementation. That's what is called the qubit lifetime, the fidelity of a qubit. Whether, suppose I create a plus qubit, how long does it remain a plus qubit? So different quantum computing companies provide different implementations, and for some it stays for a long amount of time, for some it stays for a short amount of time. So due to these errors, so and there are lots of other errors that keeps on happening on actual quantum computers, which is why when you run them on an actual backend, what you see is slightly different from what you observe in theory. But saying that, the errors are not very bad unless you have very, very long circuits in which the errors can sort of mix up from between one another. Let's suppose you have a 10 qubit circuit or 20 qubit circuit. There's a lot of interaction happening. But if you have a very simple circuit, very few gates, and then you take the measurement many times, what you will see is the distribution that you will get, this alpha bit, remember when you measure, I get a distribution, right? I get either some state with the probability, another state with the probability. So IBM's quantum computer also gives you this distribution. The distribution you will get will be very close to the theoretical distribution.
Okay, sir. So can I use the IBM Quantum Composer environment for particularly for detecting some fault or as a standard tool?
Yes, you have to understand that there are errors possible, but now IBM has released allows pulse level APIs, so you can actually do very, very fine-grained control on their qubits. You can figure out their errors, you can sort of tweak them, you can do very fine-grained control. But that's something that probably some of the speaker will talk about. There are a lot of tutorials on the web, but you can definitely do that. But there will be errors, but then there are ways to model the errors to also bound the errors. That's possible.
Thank you, sir. Sir, one more question, sir. Sir, is there any particular source for getting all this standard circuits, sir, for experimental purpose, sir?
IBM's blog and Stack Exchange would be the places where I would recommend. So these are the two places that I know that have a lot of circuits. Or so the IBM has some forum also, right? There's a Qiskit forum, and there you would see. But nowadays, all these, there are a lot of forums for, even Google has opened Circ. Their simulator, but whatever runs on the simulator will also run on the backend. So I would say that you follow the Stack Exchange forums and the blogs of IBM, Rigetti, Circ, IonQ, all of them, and you should be able to find many circuits like this.
Thank you, sir. Thank you so much, sir.
There's one question on chat. Jagvir Singh is asking, can we say Bell state is, yes, exactly. Bell state is used for teleportation, and precisely for the reason that I explained. I just did not have time to complete the entire example, but the reason is, so the quantum teleportation actually uses Bell state for that nice property. Bell state has many other nice properties also, but I just ran out of time. Any other question? Yes, Anshu Kumar, please go ahead.
So, any other question from the participants? Okay. So, it's really a nice interactive session. Thank you, sir. Thank you for clearing all the doubts of the participants. And here with this, we are concluding our first session and request all the participants in the next session very shortly. And thank you all. Thank you for joining with us. Join with us. Thank you.
Okay, so I hope I can leave now.
Yes, sir. Thank you, sir.
Yeah. Okay. Somebody asked for my email, so I'm going to paste it on chat. So this is my email. Feel free to reach out if you have any questions. Okay. Bye, everyone, and thanks for listening.
Bye, everybody.